I hope you enjoyed that little animation. I thought it was pretty cute. It's one of my favorite ones. But okay, a little bit of announcements before we begin today's lecture. As a reminder, we do have office hours. It is every Monday and Friday from 5 to 7 p.m., both in person here in this room and also online if you can't make it in person. We're like on Discord, you can just join the call or whatever. But yeah, please utilize this resource. We're here for you if you ever need any help with homework or your group shorts or just anything, or you just want to come and chat with us. We're here. So get help with your tasks. What? Chrome. Hello. Okay. Okay. How did the lab go? Not good. It was kind of rough. Well, yeah, it's okay. It's one of the more difficult labs out there. Well, okay, I'll just take over the beginning section because you're late. You're late.
Good reason.
Yeah, but it's okay. Like some common tips and notes on the homework so far that we want you to keep in mind. First things first, combining meshes versus grouping. Just understand the difference between when it is good to combine the mesh together and when it is good to group them. So as a reminder, combining the mesh means you have two meshes and you're basically turning it into one mesh, like one object. While grouping is like you're taking these two objects and they're still separate, but you're just basically like putting them underneath a folder, which is the group. So you're putting them under a hierarchy, but they're still separate things. Edge loops and multicut, so make sure your topology is good. Don't have like really weird edge loops everywhere, or like don't have like too many edge loops. Remember, one of the core tenets of topology is to only have the minimum amount of edge loops needed to uniquely define your object. So don't have too many, don't have too little. Just keep in mind your topology. Name your outliner. I don't want to see any like p cube 27, like actually. So please make sure to name things descriptively. It will help you a lot, especially when you make your sets and you put all these assets in together. It's just easy to know like, okay, this asset is called this, so therefore I know what it is. Follow the lab. If you ever have any like, oh my god, things just aren't working, like what the hell is happening? Chances are you probably skipped over some instruction. So just make sure to read everything thoroughly. And not just like look at the pictures. I know some people do that. It's okay, I get it, but make sure to follow the lab and to actually read the instructions. And also keep using Discord and office hours. Remember, we do have a homework help channel, so you could just post a question in there, and then we'll answer the question. So it's a pretty good resource. Also helps out some other students in case some other people have the same questions. Or you can come to office hours if you need more directed help. That's well. And also, don't worry, you're doing great. Okay, even if that might have been a rough homework for you all, it's okay. You're doing great. Be proud of yourself. Pat yourself on the back. Your foxes don't have to be perfect. Here's some examples of foxes from, these are past facilitator foxes. So don't worry, we're not going to take your fox and put it up here. These are some past facilitators who, they did their foxes when they took UC Bug. There's some pretty janky stuff about this, but it's okay, you know, like, don't beat yourself up if it's too bad. It's okay. Okay, on to today's lecture of topic, shading and UV mapping. Do you want to do this section?
Hello everyone, I'm Hoel. For those of you who don't know me, so yeah, let's get into it. Shading and UV mapping. Today's agenda before we get into it is like, this is a high level review of everything we're going to cover. So PBR shading, texturing, and then we're going to do some proceduralism stuff, how to like generate stuff automatically, NPR shading, lighting, and then that'll be it. But if that didn't mean anything to you, that's all good, because we're going to get into details now. What we learned so far to kind of ground ourselves is just how to do plain old modeling. So we've worked on the toilet lab, we've done the Fox lab most recently. And this was sort of taking like your basic geometric primitives and like, you know, extruding them in some ways to get the desired shape. But how do we take this one step further? How do we get like the toilet on the right, for example, and get it from something that looks like kind of like this dull, you know, kind of gray looking thing? Like the shape is fine, but it doesn't look like quite like a toilet. How do we get it to look more like something on the right here? This is what you'd expect a toilet to look like, right? It's got like the reflections, it's got like the right color. Looks like porcelain. Well, the answer to this question, oh wait, before I give you the answer to this question, another example is take a look at this like these cylinders here and like this vase kind of obscure, like it's not certain what these things are. How do we make that more concrete? Same thing. We can apply, the shading and like these different textures and what have you. So yeah, the answer is like shading. Basically, this is how we tell our render, this is what this material looks like, and therefore it should be colored this way. It should interact with light in this way. And yeah, this is like a fun little analogy to kind of like wrap your head around what texturing really means. So at the end of the day, like your models are still going to stay models. All we're doing is like wrapping them in this, again, like this shader, that it's this language that our renderer can understand that says like when I render it, it should look pretty, but in reality, like it's still just those same connections of like nodes and vertices that like are internally like very ugly. Like if you were to go inside of your objects, even when in rendering mode, they would still look like, pretty gross from the inside. So yeah, it's kind of a cute little thing. Okay, so first things first, shading. Can I get a hand, somebody to read the definition of shading for me? This block right here. Yeah.
The process of assigning shaders to your model so your renderer knows what materials the models are made of.
Exactly. Okay, so some bullet points to go along with that. It defines how light will interact with surfaces, and then shading allows us to give 3D models color and textures. Some examples on the right. So this is a model without the texture applied to it, without the shader applied to it, and then this is the exact same geometry, right? Same vertices, same edges, now with the shader applied. Gives it a lot more realism, more depth. Okay, so blue slides, this is a new thing we're doing this semester. Blue slides represent things that are like nice to know, but they're not really super critical for like purposes of, your projects or your homeworks or what have you. But here we go. So rendering, can I get a hand to read the definition of rendering now? It's like this first one here, and maybe this one here. I think I saw two. I think this one here.
Rendering process to simulate the light and colors. Renders will show you what your materials look like in the final store.
Awesome. So yeah, different renders, and like so sort of like why this is important is because different renders may simulate light and the process of shading differently. Basically, rendering is something that happens at like the render engine level. Like you might think, right? The name implies. Basically, like you can swap out renders. Like in Maya, we'll teach you how to use the Arnold render, but you could swap this out for like Pixar's RenderMan, which is like the industry standard. And then there's like these other renders like Blender's Cycles and then Lux Render, all these different kind of renders, right? But just know that this is like separate from the program, and that you need different like shaders to talk to different to different renders. Okay. Another blue slide, a note on the renders. Like I said, this is just like basically we're going to teach you Arnold, but there's also RenderMan if you take the advanced portion of UC Bug in like a later semester, or I think you could talk to your facilitators if you really want to use RenderMan. But yeah, just a note that we will be using the top one there. Okay, so a note on shading. Shading is transformative. This here is the same 3D model across these three different pictures. The only difference is that the shader that is applied to each of them. So you can get your models to look, like glass. You can get them to look like metal. You can even like add a sort of optical illusion that makes it look as if there was additional like physical detail, but still the same geometry underneath, right? And then just to like drill it in, right? Drill it home. Ton of different ways you could do this. It's not limited to just like those metals and things I just showed you. This is just like the tip of the iceberg. Is your bit?
Yeah.
Okay. Very cool.
All right, so we're going to move on to PBR shading here with this lecture topic. So as a bit of terminology, there's a lot of terminology in this. Like you don't have to memorize all the terminology, but it's just some good to know things. But what is a shader? Like the definition of a shader. A shader, by definition, is a network of attributes and textures. The key important thing to note here is the word network, and we'll get into more why like this whole network thing is important later. But essentially, it's important to know that a shader isn't a single unit of information, but a whole connection of informations and attributes together that all contribute individually to the final look. It tells your renderer how your mesh interacts with light, which then defines the material of your object. So PBR shading by definition is called physically based rendering. What the hell does that mean? Well, essentially PBR just means realistic looking materials. So we're looking in this world and we want to make materials look like how they would look in the real world. So like I'm looking at like this table over here, it looks really realistic. I have like this rock, it looks really realistic. So this is what PBR shading is, and this is what we're going to be focusing most on in this class, because it's really important to know the fundamentals of how the world works, because art is the imitation of life. So for realistic materials, we're going to be using something called the AI Standard Surface Shader. This is a shader that basically defines a series of attributes that are really, really useful for creating these realistic looks. And it's just assign it, and there's like a bunch of settings and sliders and dials you can tweak. But yeah, you can view these attributes in the attribute editor. So if you remember, when you create like a model and then you just like do the sliders for your attributes, it's the same attribute editor. The shader just lives on there. So let's go over some of these attributes and like the most important to know ones. So base, commonly called diffuse. I'll probably be calling it diffuse here because that is just a common way and how you would define this. But a diffuse of an object is basically the base color of the object. So what does this object look like without any lighting, without any reflection? It is the default color. So it is the color of a surface when lit by a bright white light. So this is the base color here. In this case, it's red. In this case, it is this like bricky color. But essentially, this is the base color. It's pretty self-explanatory. It's a color, and it's just like, okay, this is what the object looks like. Metallic surfaces have a metalness slider, which if you turn it up to 1, that means it's a metal. And if you turn it to 0, that means it's not a metal. So things that are not metals are like plastic, like concrete, like drywall, like wood. Things that are metals are like copper, nickel, like steel. So this is how you like mimic different metals. And it's important because like you need to know like, okay, well, if something is specifically a metal, I want to make it a metal. I don't know, it's kind of self-explanatory, but does anyone have questions about like metalness? Yes. It is a sliding scale, so you can make something like a half metal. Yeah. So just a bit of a blue slide here. Non-metals are actually called dielectrics, and metals are called conductors. Yeah, it's just like there's a lot of like really sciencey stuff about it because like metals can conduct electrons and like non-metals don't conduct electrons. And if you get into like really, really deep into shading, understanding the physics could help you sort of like mimic material better. But sometimes if you're just like online on the internet, you might see like it being referred to as a dielectric instead of a non-metal, or like a conductor instead of like a metal. So just a bit of terminology there. Next here is called specular. So a specular is basically the mirror-like reflection that you see on an object. So over here, like you see these like really bright highlights. This is the specular. This sort of like bright reflective area. This is also specular. This wooden texture here with like the light coming in and like bouncing off, and you kind of see this reflection of the light. That's also called specular. So specular is basically the mirror-like reflection that you see. It defines how like shiny, how close to a mirror a surface is. And there's a couple settings you can do here, like, oh, how much specular does it have? So like how strong is this like reflective property of it? What is the color of it? Roughness, which is like how rough a surface is. There'll be a slide next about that. But something that's actually like interesting to note is that there is like a specular color, right? Which is like, what is the color of the reflection? Interestingly, most non-metals don't have a specular color, which means they're just white. Typically, only metals have a specular color. So I would suggest not touching this unless you specifically are making a metal and just leaving it at white. But essentially, that's what specular is. Yes?
When we're doing this, how will it like render automatically, or is there like a render button that we have to wait for?
Yeah, there's a button. So you won't have to like wait for the full render and like wait a day for it to like render out. There's like a preview render button where you can just render in the viewport, and it's like it updates pretty quickly. So that's really, really helpful. And also, if your computer is really slow, like mine, you can render at a lower resolution, which is really, really helpful. But yeah. Specular roughness. So this defines how rough a surface is. So when the specular roughness is close to 0, it basically says it's a perfect mirror. So light bounces off perfectly, and it's just a mirror. Well, if you have like more higher roughness, then the light is a bit more random, a bit more diffusely spread. So you get this like sort of micro facet roughness here, where like it's not fully polished, it's rough in that sense. Does that make sense? Any questions on like roughness? Cool. This is also a really cool blue slide. It's like called anisotropy. Anisotropy, the word just means not in one direction. So like isotropic means in all directions, and anisotropic means not all in all directions. But essentially, like there's a lot of times where certain materials, usually metals, like almost exclusively metals, tend to have reflective properties only in one direction. So for example, here you can see that the light here kind of like spreads out in all directions really evenly. But over here, the metal here is a lot more anisotropic, and it's reflecting mostly down and very little side to side, right? So this property is called anisotropy. And you can change the rotation as well. So you're going to be like, okay, maybe this like reflects more horizontally and not much vertically. That's essentially what anisotropy is. It could be useful in like the cases in which you're making something metallic, like a trash can, like a metal trash can, or like a phone. But yeah, any questions on this? Cool. And also like someone on Monday asked this, but like, what does a 0.5 anisotropy look like, right? Like halfway between this, then it's like a bit of it spreads out, but it'll like spread out mostly vertically, so it's like an oval. So instead of spreading out like a sphere, it spreads out like an oval. Transmission. So this is used for transparent objects. So transparent means light enters an object and then goes straight through and passes to the other side of the object. So things that are transparent is basically like glass, like diamonds, like water. Those are kind of really the only like transparent objects you see, unless like you have like honey, like any fluid will have transmission because it's like transparent, or glass. So essentially you could be like, okay, I want this object to be see-through, and then that's transmission. Make sense? There's a property of transmissive objects called index of refraction. So basically, like light will enter a medium and then it'll bend. And then when it exits the medium, it'll bend again. So over here, like the light here is entering this like glass thing, and then it's bending, and then it's bending again once it exits. So this is kind of useful for like water. So water here is like you don't see straight through the water. It actually like it bends and refracts the light just ever so slightly. So if you've ever been to a pool and you kind of see those like, okay, well my hand kind of got cut off because it's like bending the light and everything. That's called index of refraction. Note that like it's not actually controlled in the transmissive slider. It's actually controlled in the specular slider. So under the specular tab, there's like a IOR, like index of refraction here, and you kind of just like adjust the number. If you're kind of curious, like what number do I use? You can kind of just Google it. There's a lot of like data sheets of like, okay, this object has this like index of refraction, and you kind of just put it in there. But yeah, this is index of refraction. It basically defines how refractive an object is. Any questions? Cool. Okay, subsurface scattering. So subsurface scattering defines how translucent an object is. So while transparency means that light enters a medium and then goes out through the other side, translucency means light enters a medium, bounces out, and then comes back out the same side it came from. So a nice visual example here is that light, these like yellow rays, the light is coming into the surface, bouncing around really randomly, and then coming back out the same direction that it came from. And this is what translucency is. So things that are translucent, all the fruit are translucent, like especially grapes. Grapes are very translucent. Your skin is incredibly translucent. If you've ever held your hand up to the light or like your hand up to the sun, you can kind of like see like slightly through, like there's a little like red glow around it. And also like your skin isn't fully opaque, right? Like your skin looks different depending on like the different lighting, because if I'm in warm lighting, then like the warm light goes into my skin, bounces around, and sort of like coats everything really warmly. So skin is like famously translucent. Flowers tend to be like ever so slightly translucent. wax, especially wax is incredibly translucent. So if we're like making a candle, like shaking a candle, it's incredibly translucent. So like this specific effect is like translucency, also known as subsurface scattering. Any questions on like what this is, when you would use it? Cool. Okay, and those are the main ones that you kind of need to worry about. There's some extra ones here. There's like a bunch of sliders and things. But here's some extra that are like nice to know. Coats. What is coats? Coats is basically this thin coats of like extra like glossy material that's like on top of objects. So if you ever think of like car paint and there's like a very thin coat of like this glossy varnish on top, that's coat. Sheen, also known as micro retroreflection, which is basically like light hits an object and then it bounces back the same way that it came from. This is for like velvety surfaces, so like velvet or silk or clothes tend to have a lot of sheen to it. Generally speaking, you will only ever use this for clothes or like those like tiny soft fur like materials that kind of like have this really like soft fuzzy look. That's called sheen. Emission is for objects that emit light. So for example, like lava or like a light bulb or like a phone, like your phone is emissive. I would not use this to light a scene though. It's not a way to like light a scene. Like I wouldn't make an object emissive so that I can brighten a room. It's simply objects that emit light, like phones or like lava, and it creates this like nice glowy effect. And then you have thin film, which is basically like this holographic film on top that sort of like creates all these like nice, cool rainbow patterns. Used almost exclusively for soap and bubbles, essentially. Yeah, so a bubble is like famously thin film. It's basically you have this really, really thin holographic soapy layer that creates all these like rainbow patterns. Questions? Quiz. Okay, what attribute out of all of these do you think is the most useful for wax? Were you here on Monday?
Yeah.
Yes. Yes, that is correct. Can you explain why?
To be honest, no. I was thinking about the hand, like
Mhm.
what you gave us. Okay, I guess I can. Because the light's kind of like going through the wax.
Mm.
It's not emitting the light, but you can like see the light going through the wax.
Mhm. Yes, exactly. So light basically goes in, but it's not transmissive because transmission, remember, the light fully penetrates to the surface, which means you can see the other side, right? Here, you can't really see the other side of wax. It just has this sort of like ethereal, glowy texture to it where it feels kind of soft and squishy. And that's a really like distinctive property of subsurface scattering. So yeah, it's not base is important because it does have a base color, but is it like the most important for determining like a waxy thing? Not really. Also, like wax can look like different colors, so it's not transmission because, like I said, it's not transparent. Like you can't see through the wax. And although there is specular in here, like you kind of see like the reflection here, it's not like a really key defining feature of wax. Quiz 2. What attribute do you think is the most useful for this cast iron pan? Yes. Is it roughness? Close. And I'll explain why in a bit, but not necessarily roughness. Anyone else? So like cast iron, right? Like what type of material is iron? Yes. It could be all three. Honestly, a lot of these do contribute really heavily to the final look. The answer that I was kind of looking for is metalness, and I'll explain why in a bit. Though roughness is a very like I do completely understand why you would say that. So metalness is important because cast iron, like iron, is a metal, which means you should turn the metal inside up because it is a metal, right? And the reason why I wouldn't necessarily say roughness is because if you took everything else away and you left only metalness, then it would just be like a perfectly shiny cast iron pan, but it's still iron, right? Like you can still clearly tell that it will be iron. compared to like if I had roughness but I didn't have metalness, right? Then it wouldn't even look like iron at all. It'll look like a rough piece of plastic, which is not anywhere close to like a cast iron pen. So that's just sort of like to think about using your brain a bit. Like, okay, I'm analyzing the materials that I'm seeing in real life. What are they actually made of? What are the properties that they have associated with them? Here, it's also not anisotropy because the light and the reflection is spreading out equally in all directions. You can kind of see like, oh, but there's like this ring of reflection. That's simply because the surface itself is curved, right? It's a curved surface, so it's going to be mostly reflecting in that area that's sort of like facing towards the light. But otherwise, like if you were to look at areas like here, like over here as well, a lot of the reflection is sort of like spread out evenly in all directions. So it's not anisotropy. And it's not IOR because it's not transmissive. Make sense? Any questions? Okay. Okay, I'll do a little demo on shading and we can have a little fun with shading here. But let me grab a chair. Actually, here, I'll just grab one of these chairs. Okay, so here I have this little Maya scene. I have this little robot here. This robot is actually the robot I made for my short when I took UC Bug. So how fun. But we're gonna go and basically, you don't have to follow along. We're gonna go pretty quickly. It's just to sort of get a visual demonstration of the different properties that we talked about. So here I'm going to assign it a new material, and the material I'm going to give it is the AI standard surface material. And you can see here how on the side there's a bunch of these properties that we talked about. So I'm just going to go and render this real quick. And forgive me, my computer is really bad. So it might take a while to render these things. I'm just going to render out this like tiny square here. But I can change like the base color here. Like maybe I could give it like a nice little red color. Once it renders, it's my computer is so bad. Oh my god. There we go. It's a nice red color. I can make it like very not rough. So I can make it like a mirror. Like if I made it a metal, I could be like, oh, there's the metal. And you kind of see how like it looks a lot very metallic here. It's like this little red metal. I can turn that back down. I can go be like, okay, what if I want to make it transparent, right? I can be like transmissive, and now it's like slightly transparent. I can increase that up a bit. So I can have this like transparent-y looking thing. Yeah, I don't know. It doesn't look that good in in here, but otherwise, I can also like show you what subsurface looks like. So if I were to have subsurface here, and like turn that like really, really far up, it kind of looks like this like gelatinous blob. Like it looks like gelatin essentially is what like subsurface kind of makes things look. But yeah, another really cool thing you could do is to look at presets. So if you're not really sure about how to make the material for a certain object, there's these presets, and there's a bunch of these presets on the side of here. So we can go and play around with some. Is there any specific preset you guys want to see?
Lava.
Lava? Okay, where is that? Am I blinds? Wait, is lava on here?
Nope.
Milk? You want to see milk? Okay, milk, replace. And that's like a nice little milky texture. Here, maybe I can increase the resolution so it doesn't look so ass. Okay, is there anything else? Okay, let's try a different one. Diamonds? Okay, where is it? A, B, C, D, replace. You get this kind of like, I mean, like, it doesn't look as good because I don't have like this super, my computer isn't good enough to have like these like rainbow colors appear everywhere. And also like a lot of the times with gemstones only look good if the lighting is good. Like you have the light hitting it from a certain angle, and it's like sort of like doing all this really cool stuff around. But it does look kind of like this like glassy, but it does look hard. It doesn't look like pure glass. Like for example, if I were to change this to say like there's a glass in here, like glass. like this looks a lot like glass, right? Like there's a very glassy look, and diamond kind of like the index of refraction is different. It looks a bit more hard and tough, a bit more rough here. If we were to change something like a liquid, that's not like milk. Let's say like oh, I think some people on Monday was like, oh, let's replace it with blood. We're gonna see what blood looks like. Iron here, what else can we do? We can do some like orange juice. See what orange juice looks like? Hey, maybe that's what orange juice does look like, Yeah, but we can actually see how like some of these objects could be like slightly transparent as well. Ooh, it looks really weird in the viewport. But like for example, if I were to like add a light in here, for example, here like this. Let me just add the light, and I'll just add the light inside the object. I'll just add the light inside the object, and I'll make it like really, really bright. Give me a second here. Boop, boop, boop. Maybe this isn't the best. Oh, it's facing the other way. You can kind of see how like there's this light that's like emanating from it because I put a light inside. You kind of see it's like translucency in here, or it's like slight transparency. If I were to change to a different material, say like something a bit like transparent, like blood, you can kind of see like it's like illuminating from there. If I were to increase the resolution so it doesn't look so bad. No, let's face it the other direction, huh? Give them some privacy a bit. Here, I'll make the light a bit bigger as well. Yeah, now you can kind of see like how a sort of like transparent material, like something a bit more liquid-like, would react to light to see if light sort of like passes through it. You can see how it has this like there's like the fall of light. It feels like a bit thick as well. Yeah, that's essentially the shading demo. I'm just here to just like show you some of the cool things you can do with shaders. Let's actually do this together on how to recreate a material in real life. Not in real life, like recreate a material in Maya. Okay, so we're gonna be recreating this material right here. Okay, so let's do our best. So first things first, right? It's wax, so we know that like subsurface scattering is going to be a really vital component to it. We also know that it is a bit reflective. Like if you see this over here, it is sort of there is this what's it called? I'm blanking. It's specular, right? Additionally, it could be anisotropic. I'm not really too sure because like the light here itself is a cone, and you can see this vertical light. So we can play around with anisotropy. It's not metallic, it's not metal, so we know that the metalness slider is going to be 0. What other things can we sort of like analyze about this? Yes, coats. Yeah, it could have coats where there's like very like thin film of stuff on top. If you think of wax, there's like that glossy grease that's sort of on top of wax. So let's take those into consideration and let's try to recreate this material. So here we have a cylinder. We're just going to use this to approximate our waxy material. Let's go and assign this a shader. So a standard surface shader. So what do you think the base color is? It's some sort of orangish color, maybe something around this sort of color. We know that, is it rough? Let's see. Doesn't look very rough to me. And then specular, we do know it's specular. We also know that it is not a metal, so its specular reflection color is probably white. Is it rough in this specular? It doesn't look that rough. It might be a bit sort of, it's actually pretty glossy. So let's go and lower the roughness slider for the specular. It could be anisotropic, but let's turn that off for now. Is it transmissive? No, it is not transmissive. I can't see through this object. Subsurface here. I will say subsurface scattering, even though it looks really cool, tends to lag out your computer. So let's hope this doesn't crash, okay? Let's turn off the subsurface. I haven't rendered yet, so I'm just changing the sliders. But let's turn the subsurface up. I don't know how much subsurface to do, so I'll just approximate it. Additionally, you have your subsurface color, which is like, does the color change when it goes into it? Let's just try white for now, and then we can sort of mess with things later. But with this, let's see what this looks like. Ooh, not good. Probably because the subsurface color isn't correct. So what sort of color is emanating from the inside of this object? This orangish color that's probably a lot darker. Maybe something like this. Maybe a bit more saturated. Maybe something like this. Or maybe there's a bit too much subsurface here. Let's turn it down. I added a skybox. Mine doesn't default come with a skybox. I added one. Okay. Let's go. It's a bit difficult to see because of the light that's added, and usually you don't have candles in broad daylight. So instead, give me a second. I'm just gonna go and add a really quick light here. See what this looks like. I'm just gonna make this light a lot dimmer, so we can sort of simulate the lighting that's here. Don't get too caught up in lighting. We'll cover lighting more in depth later. And then I'm going to go and make a point light, just like in there. Position this up here. Kind of like that. And this sort of emulates what the lighting conditions are. Obviously, it's not perfect. Here we can see that it's a bit dark. It seems like the colors here are a lot more saturated. So maybe we can go and increase the saturation of this subsurface color. It is a bit dark in value, so maybe the base color can go up and be a bit brighter. Maybe a bit more orange. Maybe a bit less orange, actually. But yeah, we can also mess with anisotropy. You can see the reflection of the light down here. Let's see what happens if we turn on anisotropy. So here, anisotropy, let's turn that up. Oh, see, the light actually goes in like a very specific direction. So if you turn this off, it's more like a circle. If you turn this on a bit more, it's going more in a singular direction. So maybe it's that sort of emulates this sort of look a lot better. And let's also try coats that was mentioned here. Let's see what this does to it. Maybe you can't see a difference because my computer is too bad. I personally don't see too much of a difference. If I like smooth mode this, oh please don't crash. Oh please don't crash. Please don't crash. Why is not showing? Okay, there we go. If I were to smooth mode this, let's see if coat's doing anything. It seems like it's not, at least for like this specific example. I think I am rendering at a lower resolution, so it's just difficult to see things. So maybe it's not as necessary. But otherwise, like the key important takeaway here is when you're looking at an object in real life, you sort of just want to identify why does it look the way it looks like that? Is it a metal? Is it not a metal? Is it reflective? What direction is it reflective in? What kind of colors are at play here? And sort of just critically analyzing the world that we live in allows us to recreate these in 3D a lot. Art is the imitation of life, after all. Yeah, and that is essentially the demo. I hope you enjoyed it. But yeah. Okay, next we're going to move on to texturing. But before that, does anyone have any questions on this entire section on PBR shading? Cool. Okay, I'll leave this next section to Joel.
Hello, I'm back. Texturing. Oh, okay. The problem. We've been manipulating sliders that allow us to control the attributes of shaders, but this applies uniformly to the entire model to which the shader is applied, right? But what if we wanted to add like more detail? What if we wanted to tell our render, you know, I want this part of my model to look this way and this part over here to look this way with a lot of control. For this, we use a different technique. It's known as texturing. Could I have a hand to read the definition of texturing right here? Anybody? Oh, hand, yeah.
Texturing is a 2D image used to alter how various attributes tile across the surface of your material.
Exactly. A shader is a network of attributes, and textures basically we're assigning. It's a lot of different attributes. Textures are inputs to shaders, but they're not the same thing. So with only attributes, we can only control a material uniformly, but with a texture, we can do things that are more like, how do I put this? I don't know, like there are different colors at different places of this mesh, if that makes sense. But more concretely, right, like a texture looks like this. It looks like a 2D image. Um, you can literally draw it in something like Photoshop, or you can procedurally generate it, and then it gets applied to your mesh. Basically, we'll get into how exactly it works, but it gets your model will like sample from the texture and then like gets wrapped around it. For texturing, we need to go over UV unwrapping. So I mentioned briefly like it gets sampled from this like 2D texture. How do we go from that 2D to 3D? This is what UV unwrapping is for. Essentially, our mesh is 3D, but our texture is 2D. So how do we determine what parts of our 2D texture get put onto our 3D cylinder or like model? This is just an example. A way to think about UV unwrapping is sort of like if you've ever done like I don't know if you guys ever had like scholastic books back in elementary school. I had scholastic books, and I had like these Minecraft like cutouts. Yeah, I like told my mom that I was gonna buy like 3 books, but I really just used the money for the 3 books to buy one Minecraft like cutout thingy. And basically, you'd like cut out the flat like like a crafting table or whatever, and you'd fold it together. It's sort of like the inverse of that. You take your 3D model and you you cut it up in such a way that you can flatten it down to 2D, and then you can take that 2D rendering, color over it in something like Photoshop, and then now there's like a mapping, right? So some applications are like cartography. Here's another example. This is just like you can imagine this mushroom here being like cut across the stem here, and then being cut like down this way, and then flattened out, and then same thing with like the top here, those 2 layers. Another cool example is like what's something that you guys are probably familiar with if the Minecraft thing wasn't relatable. Chocolates, right? Wrappers. You can always, or like in chocolate candy, you can always unravel it and then flatten it out. This is basically you can think of as like your UV map, and then the chocolate was like the 3D model that the texture was applied to. Yeah, so conceptually, that's UV unmapping and UV wrapping. Here's what it looks like in Maya. With something really complicated like a human, it can be like a little unsettling, right? You're kind of like skinning your characters. Like this rhino is being essentially cut up in such a way that it can be flattened. Same thing with the face. Gosh. Okay. You're already familiar with UV maps, whether you know it or not. If you've ever looked at like a school map, this is literally an application of UV mapping. Our world is 3D, but it's able to be sort of like sliced up and then flattened out. Another application is like in modeling, modeling like clothing, right? Like you need to first decide what parts of like your leather or whatever you want to cut out, then you cut them out, and then you stitch them together into something that's more 3D. This is just more of this. Like this is a quick like side note. This would be like a blue slide. Is it blue slide? I don't know. Basically, other ways to project down to 2D from like a 3D thing are like planar projections. Basically, literally just like squash, as opposed to doing the cutting we were talking about before. And then here you can do something that's called cylindrical projection. So like every point on the surface of this cylinder gets like shot down onto the surface of the model thing, or the model underneath, and that is like the mapping. But less applicable to us. Questions so far about UV unwrapping or texturing? All good if not. Now that you've UV unwrapped in Spirit, there was a demo, but it was like it's not worth doing. It was a lot of tedious things. But imagine in your heart you unwrapped a model here. How do we actually apply the texture that we've colored? That we've like drawn over our UV map. In Maya, it looks like first going to your model in Maya, right-clicking it, assigning a new material, we are using, for the sake of talking to Arnold, the renderer Arnold, we're going to apply an AI shading surface. When you apply the shading surface, it's going to open up this new like field in the attribute editor, and among the many options that it will like allow you to like mess with, one of them is color. You're going to click on this checkerboard box within color, and it's going to give you a bunch of options. You could assign literally like a matte color, like blue or something, but we're going to click on File, and then from there, we're going to find that the UV like texture. This is like a PNG again. You've gone to Photoshop and like colored it in or something. Find that PNG, and then it gets applied automatically. You can also, another way to do this is through a thing called Hypershade. I believe there's a lab on this, but I won't go into too much detail now. But you can sort of think of it as like this. Again, we previously mentioned networks. Basically, you provide inputs into like, it's sort of like programming a little bit. It's like this set of instructions, and then the output is like a texture. Maybe this is your way of like procedurally generating something that you wouldn't want to draw by hand. Like we'll have some examples later, but like noisy stuff, like I don't know, like the texture of like a wall or something. Hypershade, you can create nodes to wire in units of information to each other. Here, the file texture's color drives the input color for the standard AI surface shader. So this is just like more zoomed in, basically what we just went over. But you have your inputs. You can even like plug in files as inputs. So you're sampling like from a file, and then it gets fed into your AI surface shader, and that's like what generates the final look. But you'll learn to use these in more detail like through the lab. But at a high level, even though there was a whole lot of detail on how to use the hypershader, any high level questions on like shading in general? Okay, next part of texturing that we're going to cover is color textures. So color textures are textures that output color, as the name implies, right? These are usually your diffuse textures. We went over diffuse earlier. This is literally just like the same color spread across the entire figure. So these are good for a lot of things, but they tend to look kind of lame when it comes to when we want to do things like a brick wall, right? Like you wouldn't expect the brick wall to look lit the same exact way everywhere, because you kind of expect there to be some depth to the bricks, right? Like some of them are like higher than others. So this unfortunately is not like the best solution for like textures that are more detailed. Another thing that we wouldn't want to do is like literally model in the texture ourselves. I mean, you can imagine trying to like painstakingly like displace vertices to get every single like bump in like a floor pattern, right? To get those like scratchy details and all that. But that would like take forever. So what's the solution? We use data, apply that to our textures to kind of do this like for us. So to reiterate, the problem is that fine detailed models in our meshes, like if we were to model the fine detail manually in our meshes, it would create like too many polygons. So it's like a lot of manual work, and it's like a lot more processing for like our render. The solution is to store these details in texture rather than polygons. There are two primary ways of doing this. We have the bump/normal map. Basically, this simulates detail on the surface of an object by altering the normals of points on the surface. And we also have this thing called displacement maps. These simulate details on the surface of an object by altering the geometric position of points on the surface. These are more render heavy, but they tend to look nicer. Over here is an application of, I believe, normal maps. So they've, again, like they simulated the look of like different points on the mesh have different lighting properties, and so you get like this kind of like, some parts have different shading or different lighting. But to like understand that in more detail, we first have to understand something like fundamental about meshes, and it's that every single face in the meshes that you were modeling have like appended to them a normal vector. This is something you may have heard of in like your calculus class, like 3D, what's that class, like multivariable calculus. Normal vectors literally is like a arrow pointing from the surface of a face out into the world, and it just tells like our system that this is the forward direction of the face. So if light is hitting our mesh in this direction, it should be very well lit. As opposed to like if light is not hitting the mesh head on, it should be less low. And sort of to visualize like how that like why this is important, if we go back to this idea of like normal mapping, normal mapping is literally, it's simulating the look of different spots on the mesh have different lighting conditions by displacing the normal vectors, even though the underlying geometry, like the faces, have not been moved. Some ways that we actually go about like displacing these normal vectors are called, like two methods are called bump maps and normal maps. The main difference between these two is that one of them uses like grayscale version of the texture as like the underlying data to displace the vertices. It basically says like the dark of an image should be mapped to like a certain level, a certain height, or like the lowest height. Or let me rephrase this. The darkest part of your texture should be the lowest normal vectors, and the lightest part of your textures should be like the highest normal vectors. Whereas normal maps, they do something very similar, except they use RG and B, so it's not just light and dark. So it's like more information, and it displaces the normal vectors in like 3D space. So like you can visualize the differences here. This is just the regular bump map. This is like normal vector, so it's like more detail, and this is like the more standard approach nowadays. It looks like more realistically has depth, but like at a even more than those two methods, there's this other method called displacement maps or displacement mapping, which physically displaces vertices and edges, or I think just vertices and normal vectors, to get like accurate like shadows. Right? So like when you run your rendering calculations, you like simulate light. The mesh is physically like displaced. The vertices are physically displaced, so you get like proper shadows and everything like this. Whereas the past two methods, they did not have proper shadows, and they look better. But the trade-off is they're more expensive to render. Like they take more time to render. Yeah. Any questions so far? That was okay. Like the more technical portion so far of the lecture. If not, no worries. Another like kind of tad bit of information here that's kind of interesting is like you can think of these displacement maps as like mountain ranges. Like it's literally like assigning heights to each of these points on our texture, and ergo like the model. Another thing you can think of it as like waves, right? Waves are essentially just like points of water at different heights across the surface. So another way to think about it. This is what we talked about before, so I won't go into too much detail, but again, like when you're talking about bump maps and displacement maps, you're literally mapping the the darkness and the brightness of a texture to how high like the normal vector is. Roughness maps, you can, so this is a different thing we're getting into now, but another type of mapping that we can create. You can use the data textures to alter shader attributes as well. So this is a speculative roughness map, a 2D texture used to define what parts of the object are rough. So now just different parts of the shader are roughness, in like roughness have different roughness levels based off like the map we've created. Putting it all together, we take all these things like displacement mapping, texture map, the normal vector like displacements, all these different methods, right, that we discussed, and we can put them together through the node editor or the shading network, and get them all to contribute to a final shading. So like you can imagine removing just like the displacement maps, and now your shader looks more like this, but then you add it back, you add that node back, and now it's like it looks like this. So you can like kind of tune with very fine, control how you want your final shader to look like via the node editor. Yeah, so that's kind of a neat thing of Maya. And that should be it for that section. Any questions?
Yes, there's a question.
Oh, yeah.
How exactly do you add the nodes
in Maya? Yeah, so it's like a different. There's basically a part of the Maya that's called the Hypershade editor. You'd open it. I don't know the exact. Like it's basically like in the menu, right? Once you open it, every shader already comes with like a default like node, and then you're responsible for like adding different inputs. So you can. I mean, the lab will go into detail more, but right, you can like right click and then like create new node, and then like add a file as input to the AI surface tune shader, and then it sort of looks like what we showed a couple slides back, like this guy here. Yeah, but it's pretty Yeah, it's pretty hard to describe now, but like the lab will go into like more detail. Yeah. Okay. 5 minute break or?
No.
Okay, let's see you then. All right, take
Okay.
it away, sir.
I know that was a lot, and there's a lot of information, but it is important to know. Otherwise, your shaders kind of look really flat and boring, and we want your shaders to look interesting. So, yeah, it is important to know. But if it's a lot, you can always come to office hours. You can always review these slides later. The lab goes a lot more into depth about like the actual processes and how you do these things. I know we kind of just skimmed over like, hey, look, UV unwrapping, this thing exists. That'll do it. But the lab goes into a lot more detail, telling you like what buttons to press, how you actually go about doing this process. But yeah, next we're going to get into is intro to proceduralism. So if you recall, a shader is a network of attributes, and each attribute is stored inside of a node. So what is a node? A node is by definition a unit of information. So by creating like all these tiny units of information, we can link them together and use like a bunch of small different parts together in sort of like this giant like factory to make something really, really cool. So the entire concept of like proceduralism is that you make it once and then use it many, many times. Because instead of using things like using your UVs and everything, you're using logic to be able to shade something. And the same logic can apply to a bunch of different objects. So you don't have to redo this thing for every single object that you do. All you need to do is just make the shader once. So here's an example. This is a muffin shader. So by using a series of like logic together, you can create a shader that when given any object makes it look like a muffin. So when applied to a muffin, it looks like a blueberry muffin, but you can also apply it to a donut. And the logic is there to be able to apply the shader to the donut to make things look like a muffin. Make sense? Some other cool things you can do with the Hypershade editor. This is really cool artist, Mani Salguero. This is done in render, so there's not like any post processing or anything or compositing. This is done in render. Super, super cool. I don't really understand how it works, but you can check out his ArtStation. But here's just some of the things that you can do with the node editor and just combining a bunch of things together if you're really familiar with it. What we're going to be covering here is just like a couple different nodes that would be really helpful in various use cases. So the first one we're going to cover is triplanar projection. So the problem here is that UV unwrapping is really annoying and it takes a long time and it's also kind of hard. And one of the worst things about UV unwrapping is that bad UVs cause textures to look really bad. If you remember from like the UVs and the projections, depending on how you unwrap your UVs, it can cause your textures to sort of like really stretch or like shrink a lot. And this is just like the nature of UVs, and it's really annoying to try to like avoid distortion with your UVs. And additionally, with UVs, there's seams, right? If you remember like cutting up your clothes as an analogy, there are seams where the different like pieces of fabric connect together, and then you can visibly see a seam. With UVs, the same thing applies where you have these seams. And a lot of times it's just really difficult. It looks bad. So what is the solution here? The solution is triplanar projection. So it basically allows you to apply textures on any object without having to use UVs. Sounds amazing, right? It's like, oh my god, wait, UVs, why did we even learn about this whole UV thing? It does have its own downsides. So one of the upsides here is that like with UVs, like there's like this tiling that you see, like it's going in this direction more than this direction. You can kind of see the same texture like repeat itself or whatever. But with triplanar projection, you're physically placing this texture onto an object. So if you remember, like this is just a texture and you're like placing it onto the object. So you don't have to deal with UVs. And it's really, really good for uniformly distributed textures. So textures that are sort of like they look the same from all directions, but they are textures, they have like micro variations, but overall the entire shape is like, okay, they're pretty uniformly distributed. Like a lot of things like, you have your like soil, like sands, like concrete, they have these textures, but there's not like, okay, I need this specific part to look like this and this specific part to look like this. It's like, okay, I just want this texture evenly tiled across the entire surface. That is where triplanar projection comes the most in handy. So here's just like a pro and con list. UV wrapping, it gives you a lot more control about what texture applies where. However, UVs matter a lot. If your UVs are bad, then it's going to be really, really difficult to be able to texture something properly. While tri-plane projection is really useful for uniform textures. However, it's really bad for textures that require a lot of artistic control because you don't get to control what color goes where, essentially. And the upside is that it does not require UVs. Questions? Cool. The next thing we're going to cover is a really useful node called noise. So by definition, what is noise? Noise is basically semi-random values across the surface. So it's basically like static. So here is an example of noise. Basically have like, oh, there's like this white portion and this like black portion, and it's basically just a bunch of random numbers that are like kind of related, but it's like also very random. And that's essentially what noise is. And you're like kind of like, how would I ever use this? It's kind of like, what the hell? It's just a bunch of random numbers. But it's really, really useful for adding random detail because in our world, there's not many things in our life that are like perfectly the same color or texture everywhere, right? There's a lot of like tiny random variations that sort of like, okay, maybe it's brighter in this area or darker in this area. So it really, really helps break up the uniformity and makes everything look less perfect or clean and pristine. So noise is really, really helpful for that. So here's some examples of noise. This picture, actually, if you look down at the table in front of you, that is this picture. And you can kind of see how there's a bunch of really like tiny dots everywhere that sort of like break up the surface. This is an example of really, really high frequency noise. It's a bunch of random values that sort of break up the surface. There's no uniformity to this. It just is completely random dots everywhere. And it adds this really, really nice texture and makes it look less boring. Here we have this concrete texture. So this concrete is like, you have the noise of having like these dots everywhere. But if you actually look, the concrete isn't the same color everywhere. There's like a dark spot here, there's like a light spot here, there's a dark spot here, like a light spot here, right? That is an example of more lower frequency noise where you have this noise spread across a larger surface and it just adds just a slight bit of color variation everywhere. So here, this is another example with the potato. So there's like a dark spot here, there's like a lighter here, a darker here, lighter here, dark here, lighter here. It just breaks up the surface and makes everything not as perfect. Make sense? Yeah, noise is actually like really, really applicable. You can apply this to literally everything. Like almost everything in our world has some amount of random variation, and that random variation is noise. A bit of a blue side here. If you're curious, there's actually like a bunch of different types of noise. Like noise is like a mathematical function. There's like a bunch of types of math or like whatever. There's Perlin noise, which is I think the one that we just covered. But there's also like Borla noise. In Maya it's called like cell noise. But this is actually like really, really common in the real world. Like if you ever need to model something like random but looks organic in the real world, it's probably Borla noise. For example, like a delta. I don't know how many of you know what a delta is. It's like if the water it like spreads out into like a bunch of tiny rivers everywhere before it leads to the ocean. Yeah. That's an example of Borla noise. Essentially, another example could be like I don't know, like sunflowers.
A giraffe.
A giraffe? Oh yeah, the spots in the giraffe can be modeled using Borla noise. Yeah, I don't know. There's yeah, exactly. Like camouflage, exactly. So there's a lot of things in the real world that are like modeled using Borla noise. So anything like organic tends to be modeled using this type of noise. It's also useful for like stained glass, I suppose. But yeah, that's just like an interesting thing to note. Okay, next thing is a ramp. So ramp interpolates, which is by definition like it blends between two or more different values or colors. So for example, you can just think of it as like a gradient. So on one end of the spectrum, you can have one color, and on the other end of the spectrum, you can have another color, and it just blends between them like a gradient. So it like transitions between them. So this is called interpolation. And you can have different types of interpolation. For example, it's like dark in the center and then light in the corners. For example, this one is like diagonal. This one is like radial. But a ramp is essentially you have two or more colors, and you're just blending between different values. So an example here is actually the grass. So the grass here is actually dark at the bottom of the grass, but it gets lighter up at the top of the grass. So you are ramping or you're interpolating between the darker color and the lighter color depending on the height of the grass. Another example here is the rainbow. So a rainbow is actually a very like easy way to sort of think about ramps because you're interpolating between a bunch of different colors. So there's like 5 colors, and it's like, okay, this color, and then it blends into that color, and then it blends into this color, and then blends into that color, and blends into that color, right? So this is a ramp with 5 different gradient stops where you're blending between each of the 5 stops, right? So if you ever used like any art software where you've had to create a gradient, that is a ramp. Additionally, it doesn't only apply to color. Like we're on the topic of proceduralism, you can use ramps as data. So for example, here, this is perfectly opaque, and this is perfectly transparent. So if you were to take a ramp and you were to plug that into the transmissive property of a shader, then you can say, okay, I want the transmissive property to depend based on this ramp. So it'll be opaque here and fully transmissive here, and it'll blend between it. Does that make sense? Yeah. So a really, really important thing when you're thinking about proceduralism is how can we use these data textures and these textures in general to control various attributes in our shader. Usually it's just with color, but they can also apply to other attributes that aren't color as well. Questions? Cool. Yes?
Let's say you don't use any of the preset shaders and you want to use like maybe your own pad. How exactly do you like put it on a mesh?
Like what do you mean not using a preset shader? Like you're not using the standard surface, or?
Yeah.
Well, you do need a shader of some sort attached to an object. Otherwise, there's no material, right? So if you don't want to use a standard surface, there's a bunch of different like other shaders out there. There's like a flat shader, which is like a flat color. You can also program your own shaders. If you know how to code, there's something called OSL, which is Open Shading Language. You can literally like write your own shader using code. But if you just want to like make everything procedurally and like, I think you're familiar with Blender, right? I think in Blender, like everything outputs like a color. You can do that. Like there's a flat shader, which is just like a single color. It's like the entire surface is whatever this color is. And then you can just do everything there using UVs or whatever. But essentially, like if you don't want to use the standard surface, there's a lot of different options. Otherwise, you can also still use the standard surface and turn every slider except the base color down to 0. So it's only the base color that affects it. And then you just plug everything else into the base color. Does that answer your question?
Yeah.
Cool. Okay, now we'll move on to NPR shading. Look, I know there's a lot of these acronyms. It does suck, but yeah. NPR stands for non-photorealistic shading. So anything that is not PBR, so anything that is not physically based, so anything that is not realistic is called NPR or non-photorealistic. So this is like stylized shading. It's basically like you have your cartoony effects, you have your like more stylized, more art directed. So if you've ever seen like Arcane, if you've ever seen like Spider-Verse, if you've ever seen like Wild Robots or Flow, those are all examples of NPR shaders. So here's some examples from the Arnold documentation actually. They have some nice tutorials on this, and this is all done in render, including this pixel art actually. This pixel art is done in render, so it's not like post-processed. It's not like, oh, they took the render and then they made it pixelized after. This is rendered in pixel art. So it's pretty cool. There's a lot of really interesting, unique things you can do with this. Sort of get you an example of like things you could do with NPR shading. Here's an artist. He made some pretty cool, like these nice, like cool edge outlines, sort of like cartoony anime feel. You got these shaders. This is also done in Arnold. All these examples are from Arnold, by the way. But look, there's like this cool like wireframe holographic thing. There's this nice like stylized lighting where it looks a bit like, I don't know, like Van Gogh era-ish thing. I don't know. But yeah, like you can clearly tell like this isn't like a realistic thing. It doesn't look like a picture of the real world. It looks very stylized. So in order to do this, instead of using the standard surface, we're going to be using something called the AI Tune shader. So the AI Tune shader defines some useful attributes that are useful for tune shading. One of the more useful attributes here is understanding what this thing called the tone map is. So the tone map is basically the gradation between the brightest part of an object and the darkest part of an object when lit by a surface. For example, here, the tone map is saying here is the brightest part of the surface because it is the brightest part that is lit. And then here is the darkest part of the surface because it is the darkest part that's lit. And this varies depending on how strong the light is. For example, if the light was really strong, then the brightest part would cover up more space because the brighter areas are covering up physically more space that is lit on the surface, and the darker areas are covering up less. But if the light was like really, really dim, then the brightest part would be really, really small, and the darkest parts would be a lot larger. So that is essentially the tone map. It is controlling the variation of how strong a surface is lit by lights. Does that make sense? Okay. By controlling this, we can create a lot of really anime styles. So if you remember, a ramp interpolates between two colors or two values, right? So in this case, we have the brightest part of a surface and the darkest part of the surface. And we want to be able to do something to control and sort of like create this cutoff where it's like, I don't want this to be perfectly smooth like real life. I want this to be more artistically directed. So what you can do is if you were to create a ramp, and instead of saying, okay, I want to smoothly blend between the two colors, I can just be like, okay, there's just two colors only. It's a ramp with no interpolation, so it doesn't blend at all. Then what you can do is if you connect that to the tone map, you can basically say, okay, the brightest part of the surface, I want this to be this color. And then the second brightest part, also this color. And also the middle bright part is also this color. And then suddenly, if you go a bit darker, then it's a different color. And even darker than that, same color. Even darker than that, it's the same color. So now there's only two colors that are available for the tone map. And you can see here how like the brightest parts here is this color up until a certain stop, which is the halfway point, and then it becomes dark. And it's the same color the entire way through. So you see this a lot when you have like anime or cartoon sort of looks where the shadows are like a single color and the bright parts are like a single color and not have this like smooth blend between them. And this is how you can use a ramp connected to a tone map to be able to control just like how stylized things look. So here's some more examples here where if you just have a normal ramp where it just smoothly blends between the lightest part and the darkest part of the surface, then you just get the same object because you're smoothly blending between the lightest part and the darkest part of the object. But if you were to create a bunch of different stops saying like, okay, I want it to be this color and then this color and then this color, and you're basically limiting the scope of the amount of colors that can be attached to an object, then you get something a bit more stylized, or you get something a bit more of like an anime cartoon look. Make sense? Does any questions about the tone map, about connecting ramps to shader textures? Cool. Okay. Intro to lighting looked at. Okay. So before we move on here, if you're interested in NPR shading, we have a whole lab on it. It's extra credit. So you are required to do like the PPR shading lab. But then if you want, you can also learn more about the toon shader in the toon shading lab. Okay, so inherently, when you're thinking about the material and the look of an object, you kind of need a light because if you don't have a light, then you can't see anything, right? And if you can't see anything, then you can't see the shader. So shading like interacts really, really heavily with the lighting in the scene. And we do have like an entire lighting lecture. Like lighting is like a whole thing, and we do have a lighting lecture in the future. But for now, just for the purposes of like being able to see your shader under like different lighting, we're going to use something called a dome light or like an HDRI. So what is an HDRI? So basically someone goes out into the world and then they get a camera and then they capture all of the data of all of the lighting around them. And then they take that real world lighting data and then they put that into Maya as a texture. That's what HDRI is. So you basically get perfectly realistic lighting in your in Maya essentially. So it's really, really helpful for previewing how different materials might look in different lighting scenarios because you're literally getting that accurate lighting scenario. Be like, okay, the sun is coming from this direction. Maybe I have a lamppost in this direction, or like everything else is really diffused because it's like a rock surface in the pavement. And you get this really nice realistic lighting because it is captured from real life. So we're just going to recommend using this. I think We don't necessarily have a tutorial on doing just this specifically, but I will release that later tonight. There will be a little YouTube video that you can look for just like your own purposes when you're making your group work. But this entire process is called look dev or look development. And look dev is actually like an entire production like pipeline, like a job. Like you can apply to be a look development artist, right? And their sole job is to shade an object and to see how that shaded object looks in different lighting scenarios. So they're basically like previewing how like assets look in different lights. That is their sole job. It's a whole thing. But this entire thing is called look development. So if you're ever interested in working in an industry and you're interested in this type of stuff, that's called look dev. What time is it? Okay. Yeah. So here's some different HRIs. So like here, this is one HRI on the surface, and here, this is like another HRI on the surface. So you can see here how like, oh, the sun is here, but maybe there's some clouds, so it's not like that bright. Over here, we're like, oh, the sun is here, but like maybe it's super bright, so you can kind of see the sun a lot better. This is the same like shader attached to both of these spheres, and you can see how like lighting definitely changes how an object looks. So it's important to be able to preview the lighting that is going to be indicative of like your short in the final. So like if you have like a nighttime scene, then you might want to see, okay, how does my object look in the night? Or if you have like a scene that's really cloudy, then you want to see, okay, how does my object look in a scene that's a bit more cloudy?
Hello, this is just a quick tutorial on how to add HDRIs in Maya to preview lighting. So you can find HDRIs online. This is a really good website, polyhaven.com/HDRIs. You can also search this up by going to Polyhaven HDRI and just clicking on the link. And it should lead you to just a bunch of HDRIs that you can find. So there's like a bunch of these you can just find. They're sorted here. But once you find something that you like, you can click on it. And then you can make sure you download an EXR file. And you can change the resolution here. I would suggest anything from either 1K or 2K. I wouldn't go above 2K for lighting because it's a bit excessive for lighting purposes and it just might slow things down. But once you download that, you have a EXR file. So then in Maya here, what you want to do is you want to create a dome light. And then this will just create an even light everywhere, like from all directions. Here with the dome light, so if I select the dome light, I can navigate to this shape node right here. And with the color, what I can do is I can connect a file, that color. And then, so with this file, I'll just go and pick an HDR. So I already have one downloaded here. Click this, open. The color space should change automatically to raw, and there we go. Here we go. I have the HDRI in scene now, and if I render, you can see how it's applied. Here. If you're a bit confused about like clicking this button, you can also do this in Hypershade as well, which you should have done in the lab. You go to lights and the sky dome, you can graph network. And essentially this is just the EXR file is plugged into the color for the sky dome light. Okay, I hope that helps.
Okay, so just some housekeeping stuff. The workflow. So if you have like non-UV shaded objects, so you have objects that don't rely on UVs, so you're just using uniform textures, or you're like doing a lot of triplanar projection, then what you want to do is you want to model your geometry object. I like naming it like _geo for geometry. And then you take that mesh and you basically reference that into your material file. So I don't know if you guys remember what referencing is, but it's coming back now. But essentially, you're basically saying there is a link between these two files. And what is really useful about this is that person A can tweak the model while person B can work on the material separately, independently, and they don't need to like, okay, you're using this file, I have to wait until you finish using the file and then I can use the file. Because if you think about, if you're not using UVs, then you can be like, okay, my material doesn't depend on what the object looks like. So it can just be a work in progress mesh. and I can work on the material. And then once it updates and they get a newer version, then I'm able to like, okay, well, I can see what it looks like with the newer version, but the shader is still the same. So this is really useful for asynchronous workflows. And then whenever the base mesh changes, then the material can also get the update, and then you can just use this for the shader. Unfortunately, if you do have to use UV unwrapping, then you can't do that because like when you UV unwrap, you kind of need the model to be done. And if the model isn't done, then you can't UV unwrap it. And if you can't UV unwrap it, then you can't shade it to apply the textures onto it. So you'll just have to like wait until whoever's done with modeling finishes modeling. And then once you're done, then you can UV unwrap it. Because otherwise, if you UV unwrap something and then someone changes the model by like adding extrusions and stuff, then your UV map breaks. And it's really, really sad. And you have to do that entire process again. So it's just make sure if you're UV unwrapping, finish modeling first before UV unwrapping. Housekeeping, just like everything else in your outliner, please name your shaders. I do not want to see AI standard surface 27. There was a past student and she asked for help, and there were I kid you not, there were like 50 shaders. It was literally like oh, standard surface 50. I'm like, okay, so what shader is attached to this object? And just like, I don't know. And then we literally manually went through every single shader until we found the correct one that corresponded to that object because none of them were named. So please name something descriptive. You're like, oh, it's like the computer shader, or like, oh, it's like the Hoel shader. But please name them something descriptive. Also, test your shading under different lighting conditions. Ensure your UV maps don't have poor stretching or visible seams. You want to hide your seams where like people don't see your seams. For example, like if I'm wearing a t-shirt, I don't want a seam running straight down my torso. That just looks bad, right? So your seams should be in areas that no one is going to look at. For example, like the underside of an object, or like at a corner, because like you won't be able to tell that there's a seam there. And make sure there's just no stretching, because if your UVs are bad, then your texture gets really stretched out when applied to your object, and it looks bad. Color spaces, we're not going to be covering this, but it's going to be covered in the lab. There's a bunch of science that goes behind this. If you like math, look it up on Wikipedia. But we're not going to be covering color spaces, but there is like just a button that you have to click, and that'll be on the lab. And then also, like always, do not forget to delete history and freeze transformations. If anything, it's just so you don't get docked off points on the homework. It's literally like a free, it's like 2 points here. It's just click these two buttons and then you get free 2 points on your homework. It's really, really important. It's just good like workflow. Make sure you delete history. Make sure you freeze transformations. Even after you do your UV unwrapping, like you UV unwrap, there will be a bunch of history. Delete it. So just click the delete history button. All right. Questions? Coolio. If you like shading, if you like texturing, this is something you want to go a lot more advanced into and sort of like learn like really what you can do with shading. Like shading is like it's a whole thing. Here's some like cool software you can use. So Substance Painter, it's free for students. It's a part of the Adobe suite. This basically allows you to paint directly onto a surface, like directly onto a mesh. It's super nice. It's basically like the industry standard for anything in like the games industry is done using Substance Painter. You can use like Photoshop layers to like paint on like surfaces and stuff. Very nice. Yeah, it's highly would recommend if you want to get into shading. It's not too complicated of a software to learn. We do have a lab on it. It's one of the advanced labs, but it's super useful. If you like the proceduralism section that we talked about, and you want to be like, okay, how do I make shaders using logic? Then Substance Designer is a really nice one. You basically, the entire software is how do I make procedural textures? You create a network that defines a texture and you can apply it to any object. So it's super cool. There's Mari. So if you want to get into like animation, into film, into VFX, Mari is the de facto like software that is used for every single shading everywhere in all of film. Unfortunately, it costs a bunch of money, so that is just big sad. But it is something that is like really nice. It's basically like a combination of both Substance Painter and Substance Designer together on steroids. It's like a really like intensive software, but it's pretty cool. Other alternatives, you can always use Photoshop. It's kind of ass, but you can use Photoshop. And then Instamat. If you hate Adobe, because Adobe evil company, you can use Instamat, which is basically Substance Painter but not Adobe. Also, I think they have a perpetual license, so no subscriptions. Subscription evil. They do have a perpetual license. It's a tool bag. Armor Paint is nice. It basically allows you to paint directly on a surface. It has less features than Substance Painter, but it's a free. So if you ever graduate, 3D Coat, Textura, also the same thing. It's really nice. It's free. Yeah. So this is if you're ever want to get interested in it. Additional reading if you want to learn more about like shading theory, about like the theory of how shaders work, how like certain materials and certain looks are achieved. CG4 has a nice shading theory lesson. This is not in Maya, it's in a different software, but a lot of the concepts transfer over. There's the Adobe PBR guide, which is really, really useful if you're trying to understand how do PBR surfaces work? How do I make something look good in a PBR surface? What are all the different things that contribute to a photorealistic look? They have a really, really nice guide on this. Arnold documentation, looking at the documentation for the software, every single shader with examples is listed on here. You could just kind of like go through these and see like really cool stuff. They also have a lot of tutorials that you can look at to sort of like achieve certain things that are really cool. So highly recommend just looking at the documentation. And then Polycount. Polycount is like a group of like artists that do like a bunch of modeling, but they have like texturing tutorial lists of like a bunch of like, oh, how do I achieve certain effects in it? Really nice. They also do like contests sometimes if you ever want to participate in that. Okay, homework. Your homework individually is to submit the basic material. Oh, this is not up to date. Okay. For extra credit. There we go. So you submit the basic materials lab, and then if you want to do the toon shading lab, additionally on top, that will be extra credit. That's basically worth one full homework assignment. And also like these recently went through like a whole like rewrite for it. So they should be a lot better now, but also there might be a bit of things that are like confusing, or maybe there's like a missing file image or something that you won't be able to access. So I don't know. But please, if you notice something that's wrong, if you notice the wording's bad, spelling mistakes, or it's just confusing in general, you don't like it, please let us know for feedback so we can improve for future semesters. And then your group homework is to shade your models and props and to render a single frame. All right, so good luck, have fun, and yeah, today's keyword is headphone button.